Good morning. I'm Vishweshwaran Karunanidhi from Space. We're based in the Netherlands. I'm an RF engineer and a business developer in the company. The original presentation was supposed to be given by Jeroen, but then, yeah, apologies for that. But then I'll be presenting our roadmap on low frequency radio astronomy in lunar orbits using CubeSats. So this is going to be the outline of my presentation. I will not be talking much about the science of the missions. We are mainly the industry partners, and we work along with the consortium of science and university partners. So I will be mainly focusing on the industry perspective of such missions and how it's going to benefit us. So I'll be starting off with why radio astronomy for CubeSats. Then I'll be speaking about some of the mission concepts we're working on right now. Go into our roadmap where we are looking at in future in terms of performing radio astronomy in the lunar orbit and the outcome for our company in general. A small introduction about our company. So the company is basically a CubeSat company. It was established in 2006. It was a spin-off from one of the nanosatellites that was developed from Technical University of Delft, which is Delphi C3. So the people who were working on the mission actually went on to form this company. And from that on, one thing to mention is Delphi C3 was actually launched in 2008, 2 years after the company was formed, and it's still operational. So that's something to mention. We're basically a vertically integrated organization. So basically, we kind of develop our own subsystems for the missions. We are a bit self-sustaining in terms of developing all the required subsystems for the missions that we develop. We also support complete satellite missions. So we provide customers satellite platforms that can be used for their missions. So basically, the customers can work on the payload and science of the mission. And we provide the bus for the mission, and we are also launch support. We also provide launch services. We kind of tie up with launch providers to actually deploy CubeSats in space, and also we perform satellite operations. So we also have our own ground stations. We have about 27 ground stations installed at different locations around the world. So far, it has been mainly the VHF and UHF, which are mainly popular for CubeSats, and we have also moved into the S-band ground station. And we are about 75 employees, and the headquarters is located in Delft, and we have one office in South Africa and one in UK. Okay, moving into why we chose radio astronomy for our missions, and I'm sure you must be aware of quite a lot of large arrays that are already present, which may perform radio astronomy terrestrially. But there are certain limitations when it comes to a different spectrum that you want to actually view. And we are mainly interested in the low frequency region. And we are missing quite some data based on it. The reason why we actually need to go into space to perform these measurements is because the ionosphere or the Earth's atmosphere itself is actually limiting us from doing these measurements from the Earth. So this is actually a very popular graph showing the frequency versus the atmospheric opacity. So the region that we are mainly interested in is quite opaque, and that is the reason we actually have to go outside the Earth's atmosphere to perform these measurements. And where we look at ourselves at some point of time is basically have a swarm of nanosatellites orbiting the lunar orbit and performing interferometric measurements on the far side of the moon. So basically, what we're doing here is we're using moon as a shield from all the noises that are generated from the Earth, which prevents us from performing these measurements on the Earth orbit and doing the interferometric measurements on the far side of the moon. So basically, the idea is to have a swarm. Basically, I'm trying not to use the word constellation here because there's a small difference here, because in these missions we need to know the relative positions and attitude of the satellite only during the measurement. We are not controlling the positions of the satellite to form a particular constellation. So that we kind of have an advantage in not trying to control the position. Only thing is because it's an interferometric based measurement, we just need to know the attitude and the relative positions of the satellite while performing the measurements. Yeah, a similar slide, I think Roger already showed this, but then this kind of shows our roadmap towards what we want to achieve finally. So we are already working on NCLE mission, which actually stands for Netherlands, China, Long Wavelength Explorer. So basically, we are developing a hosted payload on this mission, which will be flying early Q1, Q2 next year to the moon orbit to perform, which will actually be carrying our payload, which will be performing the interferometric measurements. So from there on, we see ourselves moving into SysNova, which is going to be more of a feasibility study and actually making our subsystems mature enough to fly into the moon orbit. So here we would be validating our own subsystems to see if it can withstand the harsh atmosphere that we would be expecting in the lunar orbit. So from there on, we would be moving into the Alpha mission, which is basically the swarm mission, which is going to fly into the lunar orbit. And yeah, this is basically the roadmap we see for our lunar mission. And of course, we're not doing it alone. As I already said, we are mainly the industry partners, and this is the consortium. And you can see that it's a nice balance of industry, science, and universities put together actually. So going more into the NCLE mission, which is right now going on, we would be flying along with Chang'e satellite, which is supposed to be launched next year. And ours is a hosted payload over here, which would be carrying the interferometer. And ESIS is actually responsible for developing the three monopoles you see over there, which is the deployed monopole. And basically this one is actually the hosted payload that we are developing right now. And just to give an idea of the status, last week we successfully completed electrical interface testing along with the main satellite. So as of now, the schedule is still on for it to be launched sometime beginning of next year. So here already what we are doing is we are validating some of our subsystems in this mission. So the one would be the antenna system and also the data processing unit. So here we are actually using the existing onboard computers that we're using for our nanosatellite missions and performing some modifications to it to actually fly on this mission. Of course, the amount of data that it's going to generate is quite a lot. So we are not actually looking at having our own downlink, but it would be shared along with the main satellite. So the main satellite will actually be relaying the data that is actually generated by the payload. So next, going into CLE, which stands for CubeSat Low Frequency Explorer. As I already said, it's a part of the SysNova feasibility study. So here we are moving from actually miniaturizing the payload, because the payload at present is not completely developed in the form factor of a CubeSat. So that we will be first looking at miniaturizing the payload, and then also validating all our other subsystems to put it into a 12-unit CubeSat. And the idea is actually to have three CubeSats launched to perform independent autonomous interferometry, and then basically intersatellite links to process the data that's collected from the satellite. So here, the main challenges that we see as an industry is actually to develop these intersatellite links and ranging capabilities, which are right now not present in the CubeSats. So these are the main challenges we look at in this mission. So from there on, we're going towards something to mention here is, again over here, we are not going to have a direct link to the ground. We are depending on the relay. But then, if we have to move on to our own mission of Alpha, we have to also go into actually having our own communication link to the ground. And over here, as you can see, we are looking at somewhere between 100 to 200 satellites being launched in the lunar orbit. And then, of course, every time a swarm of satellites that go into the far side of the moon, it performs the interferometric measurements, and then it is relayed back to the Earth when it comes to the other side of the moon. Yeah, the main challenges we see here are, again, the EMC, of course, the first one is the miniaturization that we are already looking at in SysNova. The second one is the EMC issues. Of course, the frequency range we are looking at is below 30 megahertz, and this range is quite sensitive because the whole satellite itself can act as a big EMC issue to the measurement. So we have to actually develop an RF front-end which is not susceptible to kind of interferences. And of course, relative positioning and active determination is still going to be a challenge because it's going to be a bigger number of satellites and larger amount of data that's being generated. And of course, the intersatellite links. Intersatellite links over here is going to be, we are still working on the mission concept where we want to see if we want to have a single node kind of communicating with all the other satellites, or we want to have a redundancy in kind of making all the satellites independent and kind of communicating with each other. And yeah, that's where this one comes into picture, where we want to do a distributed processing because we don't want to have a single node failure, because that, if you want to have like a single node doing all the processing, and it could actually lead to a single node failure. Right? So yeah, that's another challenge. And of course, autonomy is required over here because it is quite challenging to envision something that is going to work in lunar orbit, perform the measurements on one side, and when it comes onto the other side, communicate back to the ground. So these are some of the challenges we are looking at and focusing right now on solving them. So basically, we are engineering, or basically an industry, and why we think such deep space missions are very important to us is because of the outcome of such mission. Because of course, it's not going to stop with just the lunar mission. The subsystems that are going to be developed for these lunar missions is only going to mean that the subsystems that we would be using in low Earth orbit is going to get more reliable. So that is one of the main reasons we see spin-offs as something very attractive for us. So of course, in NCLE, we already would have kind of validated our high throughput processing and antennas, and in SysNova, we would kind of would have validated our subsystems for these missions. And when it comes to ALPHA, I think the autonomy of the satellite and the intelligence that we are actually providing to the swarm is something that we can take off and use it in lower orbit. So these are mainly the takeoffs or the spin-offs that we see from such missions. And of course, there's the conclusion, and of course, we don't look at stopping ourselves from lunar missions. We would like to be more like producing satellite buses which can help customers develop just the payload and work on deep space missions. And I think, yeah, that is where this, the whole thing is appropriate for this workshop, I guess. So yeah, that was my presentation. Thank you for your attention. And yeah, I would take up some questions because I'm not the main author. I would say if I'm not able to answer, I would really direct it to the main authors and would get back. So I'm open for questions.
Hi, I'm kind of curious about what is the accuracy of your the separation between the satellite and autonomy, and what would be your goal for the particularly for interferometer?
Yeah, of course. We look at the wavelengths; they are in the order of 30 megahertz. So, of course, we do have a little bit of margin when it comes to ranging, but we are still looking at what is actually a resolution that we can fix on, and it's not yet determined or yet. We're still working on what is the ranging accuracy that we need for it. So we still don't have the numbers for it, but yeah, probably sometime soon we will be coming
So I have a comment and a question, which is more of a general question. The comment is I don't think you need constant intersatellite links for radio interferometry. Radio interferometry can be done on the ground after the fact. It does not have to be real time. And the second question is, why can't this large constellation be done as a swarm of opportunity? A swarm of opportunity. If you guys flew the first 5 to 10, and then nations from around the world put the other ones in to a similar orbit with similar communication protocols, you could build it a lot quicker than you could relying on one nation or one entity to do it. Just a question.
Yeah, regarding your first comment, yeah, it is possible to do it on the ground, but what we see is the amount of data that is generated is quite a lot. So we would like to keep it autonomous and do most of the processing in the orbit and then dump it onto the ground. So that is where we would like to have our processing mostly done in space. So that is one of the reasons. And sorry, regarding your second question, it was about forming a bigger consortium, I would say.
To form a bigger constellation, have a conservation of opportunity. Here's the standards, tell people how to get into the orbit, how to communicate, and have the world show up to build this massive radio astronomy facility.
Yeah, that's something that we have been doing for QB50, I would say, which is actually going on right now. This is still at a concept level phase right now, and we are looking at subsystems for it. And I think down the timeline, we might even look at having more partners for such missions.
Okay, well, thank you very much.
Thank you.